Welcome to lecture number 20, Working Principle of Synchronous Motor. Myself, Dr. Satyadharm Bharti, and I will be guiding you through this comprehensive discussion on synchronous motor. At the end of the lecture, you will have thorough understanding of the construction, the operation, application of synchronous motor. We will go through various types of excitation, normal excitation, under excitation, over excitation. To start with, let me connect with previous lecture, lecture number 19, in which we have gone through the construction of synchronous machine. Actually, the alternator and synchronous motor, they are all same as far as the construction is concerned. In alternator, we are feeding mechanical power. As a result, it is generating the output and hence it is termed as alternator. In case of synchronous motor, we are feeding power, electrical power to the machine and the motor starts rotating at synchronous speed. So, we have seen in yesterday's class that we are having salient pole type rotor and cylindrical type rotor. For demonstration purpose, today I am having one educational demo kit. I am having this slip ring type assembly. These are the slip rings. You can see 1, 2, 3 and 4 slip rings. One for R phase, one for Y phase, one for B phase and the last one is for neutral. So, we are having 4 slip rings and the armature, it is having a smooth surface. You can visualize this surface is smooth. So, here of course, this is armature of a small rating machine. We have seen that in heavy duty bigger machine having alternator having higher rating. In that case, armature is kept on the stator part, on the outer part, whereas in the rotor we are having DC excitation. Since this is armature of a small machine, so here it is kept on rotor. On both sides we can see this is the shaft, it is supported with the help of bearings and armature winding is provided in these slots. Slots are visible and you can see the winding also inside these slots we are having winding. And the winding is designed in such a way that number of poles of the stator, number of poles provided by the field winding is same as number of poles created in this winding. So, we have seen construction of synchronous motor. A synchronous motor consists of two main parts, the rotor and the stator. Stator, of course, it is a stationary part and the rotor is rotating part. The stator consists of 3-phase winding which is connected with 3-phase supply. The winding is distributed in a specific manner to produce the rotating field. The stator winding is designed to produce a sinusoidal flux distribution and in rotor it has DC supply which produces a constant magnetic field. And the rotor is designed to operate at a specific speed which is known as synchronous speed. So, the rotor can be either salient pole type or cylindrical type. Now, we will discuss the principle of operation. The principle of operation of a synchronous motor, it is based on the interaction between rotating magnetic field and the field produced by the stator. Field produced by stator, it is constant magnetic field. Now, the term synchronous speed. The synchronous speed is the speed at which the rotor rotates in synchronization with the rotating magnetic field. The synchronous speed is determined by the frequency of the supply and the number of poles of the motor. The synchronous speed is given by the formula Ns is equal to 120 F upon P. Ns is equal to 120 F upon P, where Ns is the synchronous speed, F is the frequency of the supply and P is the number of pole for which this machine is designed. Now, about the torque production, when the rotor is rotating at synchronous speed, the magnetic field produced by the rotor interacts with the rotating magnetic field produced by the stator, resulting in the production of the torque. The torque produced, it is proportional to the sine of the angle between these two magnetic fields. Now, let me explain this thing in detail. Suppose I am having one shaft. Suppose one person comes to me and says, I want to rotate this shaft, I want to rotate this. And suppose I am person of mechanical engineering. What I will say? Okay, connect this shaft to the turbine. It may be steam turbine, water wheel turbine, Francis turbine, Pelton turbine. Or you may connect it with diesel engine, 4-stroke engine we are having. In automobile vehicles, what we are doing? We are converting that fuel energy into mechanical energy. Now that person asked me that I want to rotate this shaft with the help of electrical. So do something so that electrically I can rotate this. Okay. So what I am suggesting, suppose I am having one permanent magnet. This is the north pole, this is the south pole, and I am attaching this to this shaft. So now we are having this north pole and south pole. I am attaching one permanent magnet with this shaft, and outside this I am keeping one permanent magnet, C-type magnet, horseshoe magnet. Suppose in horseshoe magnet, upper pole is say south pole, lower pole is north pole, and this shaft is placed like this. I am dropping this rotor, just I am holding this magnet only. This is north pole, this is south pole, and here what I am keeping? Upper side, this is south pole, this is north pole. So what will happen? Now the north pole will be attracted by the south pole. So there will be production of some torque. This rotor will now try to rotate. Problem is solved. Yes. There is torque between the stationary outer magnet. This is south pole, this is north pole. South pole is attracting north pole, and hence the shaft is rotating. But what will happen after some time? This is south pole, this is north pole. North pole will lock with south pole, and now this is the zero torque position. Of course, this rotor has rotated by some angle. The axis passing through the center of this field, this is the axis of rotor. This is south pole, this is north pole, this is the axis of field of the stator, and there is certain angle between these two fields, delta. When the delta will become 0, what will happen? Now this is zero torque position. Now it will stop rotation. Now that person who came to me, he want continuous rotation. Now what I will suggest? I will say, you keep on rotating the outer magnet, and then this inside rotor, it will follow the rotation. So what exactly I am doing? I am simply shifting the problem. Initially, the problem was to rotate one shaft. This shaft I had to rotate. I am asking that person to rotate the outer magnet, and by the interaction of these two fields, the rotor shaft will continue to rotate. Now the problem is not solved yet. So for that purpose, I need one rotating field such that I have to not rotate one external this field physically, and for that we are having arrangement, nice arrangement. Just recall the construction of induction motor we have seen in the lecture number 16. The outer stator In that stator, what we have done? We have placed 3 windings 120-degree electrical apart, and we have seen that when 3-phase supply is fed to the stator of that induction motor, a rotating magnetic field starts rotating. So, we need not to rotate anything physically, simply we are feeding the AC power and we get the rotating field. The speed of the rotation of that rotating field will be given by Ns is equal to 120 F upon P. Suppose we are considering 4-pole structure and frequency of the supply is say 50 hertz, then 120 into 50 divided by 4, we are getting 1500 RPM, 1500 RPM. At the speed of 1500 RPM, that resultant rotating magnetic field, it is rotating. In terms of revolution per second, 1500 divided by 60, 25 revolutions per second it is rotating. Now suppose this is the south pole and north pole of the rotating magnetic field appears here, there will be attraction. But since it is rotating very fast, very soon south pole will appear here. There will be force of repulsion because this is south pole, this is also south pole. So, what will happen? It will feel some torque, positive direction and then in opposite direction, and due to moment of inertia, it will not rotate. So, what we have to do? We have to, by some external means, we have to rotate this inner magnet at a speed very close to that synchronous speed. And for that purpose, similar to the induction motor, we provide dampers winding on these in this central part, rotor part. So, synchronous motor does not have any inherent starting torque. Initially, we have to rotate the shaft with help of some external means, either by pilot motor or by some arrangement like damping winding. And then when the speed of this is say about 1460 RPM, very close to that synchronous speed, now at that moment we will switch on the DC supply, we will switch on the excitation of that field winding. Initially it is simply rotating without any field. When it is rotating at a speed very close to synchronous speed, we will feed DC supply to this, and then one fine moment will come when this field winding will get locked with the field produced by the stator winding. At once this link is established, now this rotor is bounded to move, bounded to rotate in synchronous speed, the speed which is produced by that. So, this rotor will rotate at synchronous speed, it will remain in sync with that field produced by rotating field produced by the armature. And this is the beauty of synchronous motor. Synchronous motor always runs at a speed 120 F upon P, irrespective of the load. If the load is increased, even then it will maintain the speed, synchronous speed. In case of induction motor, what happens? If the load is increased, the speed of the shaft will decrease. But in case of synchronous motor, it is not so. At once the rotor is locked with rotating field, now it is bounded to rotate at synchronous speed. Let me explain this by one example. Suppose, recall the film Sholay, Gabbar Singh riding on the horse, and by some rope he has tied up Dharmender ji. Now Gabbar Singh on the horse. Dharmender ji is tied up with rope. So what is the speed of the Dharmender ji? Speed of Dharmender ji is equal to speed of the ghoda, the horse. So long that Dharmender ji is tied up with the rope, speed of Dharmender ji is equal to speed of horse. So initially Dharmender ji is following the horse. After some time what will happen? Speed of horse is more. So Dharmender ji will kneel down. Jeans will be torn. But even then, since the rope is intact, speed of Dharmender ji fallen on the earth is equal to speed of the horse. There is only one possibility: when this link is broken, when this rope is broken, then only Dharmender ji will stop and the horse will continue to move. Similarly, in case of synchronous motor, at once the rotor is locked with that rotating field, it is now bounded to rotate with synchronous speed. Very good. Now we are moving to next part, which is excitation phenomena in the synchronous motor. Okay. So we will discuss power factor of synchronous machine. Power factor can be controlled by field excitation. To start with, just consider one black box. This is the box. What is inside, I don't know. Simply I am having two terminals. And suppose inside this black box we are having an electromagnetic device. It may be anything, solenoid valve, it may be transformer, any machine, induction motor, anything. If any electromagnetic device is there, it has to draw certain current from the source. Just recall the phasor diagram of transformer. What you have seen? At no load, it draws magnetizing current I mu to establish the working flux phi. Can you recall that? Phi flux is there in the same line, I mu, magnetizing component of current, magnetizing component of no load current. And what is the angle of that no load with terminal voltage? It is 90 degree. So that means any electromagnetic device, it draws lagging volt ampere from the supply in order to establish the working flux. If it is not drawing any lagging current, that means there is no establishment of flux. So if it has to magnetize, necessarily it has to draw lagging volt ampere. Now we know that synchronous motor is doubly excited machine, doubly excited. The armature is being fed by AC supply, the field is being fed by DC supply, and the resultant flux inside this, it is due to combination of both the flux. Resultant flux phi r, it is sum of phi f and phi a. Yes, phasor equation it is there. Phi r is equal to phi a plus phi f. Now, if we are maintaining constant voltage, Vt is constant. For constant voltage, the requirement of this resultant field inside this machine, it is also constant. It is given by phi r is equal to Vt divided by root 2 pi f kW NPH. if the supply voltage is kept constant, so numerator is now constant. In the denominator, what terms we are having? Root 2, it is constant, pi constant, f frequency, it is also constant, NPH, at once the machine is designed, number of turns per phase, it is also constant, Kw, depending on the pitch factor and distribution factor, Kw is product of Kc and Kd, it is also constant. So, requirement of phi r is constant, and this phi r is being created with the help of phi f provided by DC and phi a provided by the armature. If the field winding alone is sufficient to establish this much flux, then what is the requirement of phi a? There is no need. In that case, the synchronous motor will not draw the lagging volt ampere, and since it is not drawing any lagging volt ampere, it will work at unity power factor. So, for this particular case, the type of excitation is known as normal excitation, normally excited synchronous motor. Now, if the required flux are phi r, flux produced by DC, they are somewhat less than that. So, the difference amount will be fed by phi a. Since armature has to establish certain flux, definitely what will happen? It will draw lagging power factor, lagging volt ampere from the supply. So, in that case, the synchronous motor, it will operate at lagging power factor, and this type of excitation is known as under excitation, under excited synchronous motor. And now the third case, if the field is producing more flux than phi r, requirement is phi r, field is producing more than phi r, then it has to be demagnetized. So, instead of drawing lagging volt ampere, now the armature will take leading volt ampere, and in that case it is over excited synchronous motor. It is type of excitation in that case is known as over excitation. So, we are having normal excitation, under excitation and over excitation. Now, we will understand very important topic of synchronous motor, the behavior. We will study the V curves and inverted V curves of synchronous motor. We will start with the phasor diagram of synchronous motor, and then we will see the effect of increase in excitation on the power factor of the machine. So, get ready. Okay. So, now we will study the effect of field current on the power factor of synchronous motor. So, we are starting with well established relations. Power P is equal to Vt Ef upon Xs sin delta, which is equal to Vt Ia cos theta. And for the phasor diagram, we are having relation Vt is equal to Ef plus Jia Xs. Of course, here Ra, resistance of the armature, it is neglected. With the help of this relation, we will establish the V curve for synchronous motor. So, starting with, suppose I am maintaining constant voltage, Vt is constant. Suppose this is Vt, voltage phasor. Initially, this Ef is produced by field excitation. Suppose field excitation such that this is the magnitude of EF. This is EF. That means if we add JIA axis in this EF, we will get VT. So what is JIA axis? This phasor will be JIA axis. Since this is JIA, direction of JIA, so direction of IA will be perpendicular to this. This is IA. Angle between current, armature current and VT, it is known as theta. The angle between EF phasor and VT, it is known as delta. So suppose this is the first case. Since this is first case, I am marking this as EF1 and this is IA1, this is JIA1 axis. What will be the equation? VT is equal to EF1 plus JIA1 axis. This phasor plus this phasor is equal to terminal voltage. Now this terminal voltage is constant. For constant power output, since VT is constant, axis is constant. So now this EF sin delta terms, this should be constant. So in this diagram, what is EF sin delta? This angle is delta. Of course, since this is marked as suffix 1, so this is now delta 1. So in this, this distance, this is equal to EF sin delta 1. This is right angle triangle. Consider this angle delta 1. This is right angle triangle. So this is equal to EF1 cos delta 1 and this is equal to EF sin delta 1. So what I am doing? I am preparing one locus in this diagram. This distance is equal to EF sin delta. To maintain constant power with constant voltage and by design axis is also constant, EF sin delta must be constant. Now if I am increasing the excitation, if DC excitation is increased, magnitude of this EF will increase, but it will increase in such a way that tip of the phasor will always lie on this locus. So for certain excitation, initially what we have discussed, it is under excitation. For particular value, say the excitation is such that this is now new value of EF. So this phasor is marked as EF2. EF2. According to this relation, Vt is equal to EF2 plus JIA2 axis. That means this is EF2. So this phasor is JIA2 axis. Since this is the direction of JIA, so direction of IA must be in this direction, perpendicular to that. So IA will change, but it has to maintain this relation. Since Vt is constant, so IA cos theta should also be constant. So if I am drawing a line like this, and this will be the locus of in this triangle, this angle is theta. So, this is Ia cos theta. So, this distance, this is equal to Ia cos theta. Since we are changing the excitation, we are increasing the excitation, this is the case of normal excitation. So, in that case, Ia will be perpendicular to this JIA axis. So, this is magnitude of IA. I am marking as IA2 because this was EF2 and this was JIA2. So, this is now new value of IA2. Magnitude of theta, it will become 0 because it is the angle between Vt and Ia. So, theta is equal to 0. So, this is the value of Ia2. Now, if we go on increasing the excitation, again EF will increase. Earlier it was this much, then it was like this, then it is increased to this, it is increased to this up to normal excitation. Now, it is, if it is beyond this, suppose this is the value of EF, new value, so I am marking as EF3. This is the case of over excitation. Let me repeat once again. This was under excitation, normal excitation, now this is over excitation. To maintain this relation, EF3 plus JIA axis. So, that means I have to add this phasor, this is equal to this new phasor, this is JIA3 axis. If this is the direction of JIA3, so the direction of IA3 will be perpendicular to this. I am making this angle as 90. So, this is now new value of IA3. Angle between Vt and IA3, this angle is theta 3. So, IA3 will change, but it will maintain the relation. Ia cos theta will remain constant. So, what we have seen? We have seen initially value of Ia was more. When we have increased the field excitation, it came somewhere here, then it came somewhere here, then like this, then like this. So, we can observe that magnitude is continuously reducing. Magnitude of Ia, it is decreasing. After some time, it is increasing. So, if we plot one graph between Ia armature current and the excitation field current. So, initially under excitation condition, certain value of Ia was there. Then the magnitude of current is decreasing with increase in field current. So, it is coming like this. After some time, it will start increasing. So, this behavior, since it resembles in English alphabet V, that is why the curve, the relation between Ia and If, this is known as V curve. Suppose this is for no load. No load was connected with the synchronous motor. If we plot for half load, then the shape will be something like this. For 3/4 load, shape is something like this. For full load, shape is something like this. So, this is the effect of change in excitation on the armature current, as well as we can see the effect on the power factor also. If on this axis, if another curve is plot showing relation between If and power factor, then power factor say 0.6, 0.7, 0.8, 0.9 and unity power factor. This is the condition of unity power factor, because at that moment Ia2 is in phase with Vt. So, the shape of this will be something like this. This is for no load. For half load, it is like this. Then for 3/4 load, it is like this. For full load, it is like this. So, this family, this is known as inverted V curve. It is the relation between field current and power factor. Hope this is very clear to all the students. In today's class, we have gone through the constructional detail, working principle of synchronous motor, types of excitation, under excitation, normal excitation and over excitation, and at last we have seen the effect of field current on the power factor of the synchronous motor. Thank you.